Okay, today we're going to hopefully finish talking about logistic regression. Reminder, what we were doing in the last week or so is we started to discuss a new type of model, right? And in this type of model, we're trying to predict a categorical variable, right? Response of type yes, no, true, false, default on the loan versus not default on the loan, etc. based on some predictors. It's always based on some predictors, right? And here is the tool matrix, right, that we started to create. We said that if target is categorical variable, then it can be classification tree, what we learned at the beginning of the semester, or it can be logistic regression. And this is the case when your predictor is continuous variable, right? So today we're going to actually extend that and see if predictors are categorical variables, okay? Or a mixture of both, categorical and continuous. So let's open up JUMP again, all right? And go ahead and open up the same file that we used in the last couple of classes, Universal Bank CT, okay? So in this file, in this data, what we're trying to do is predict the personal loan, yes or no, 0 or 1 type of response, based on all these variables. And we said that income is the most important one, probably, right? Because people have high income, they're likely to get a loan from the bank, a lot more likely to agree, right? Low income, they don't have that luxury. Okay, but other things could be important. And note that zip code is actually excluded, right? So zip code was originally part of this data set, but now there is a stop sign right there. That means that we're not going to actually use the zip code as a predictor. It actually brings an interesting question, right? Data analysis is one thing, but let's kind of talk about that briefly. The results could be not exactly usable 100%. In what case? In which cases? Let's say I'm running the model which will predict for me, for the bank, what type of loans will default and what type of loans will not default. Okay? And I'm throwing all the variables into the mixture, right? And let's say the model tells me that males are less likely to default on the loan. So females are more likely, therefore females are perceived as higher risk. And what banks do when something is perceived as a high risk? What do they do? Increase interest rates, right? You're taking more risk, you should get more reward. So therefore, what can happen is two people come in, okay, one is male and another female. I'm running the regression, same thing, right? And I'm telling the male, hey, I can give you a loan at 3%, and female, I can give you a loan at 4.5%, right? The question becomes, what the hell? And the answer is, my model tells me, right? My model says that you're high risk, therefore, oopsie daisy, I have to charge you more interest rate. Is that legal? Not exactly, right? Because there are multiple laws in place that basically tell you that you have to treat everybody equally, right? Everybody should be treated the same. There are multiple laws, like equal housing opportunity, right? Like male is less likely, for example, or female is less likely to be overdue on their payments, right? So you cannot charge different rent to different people regardless of their, race, gender, religious beliefs, etc., etc. But my model may indicate that this is the case, right? So what do I do in these cases? Okay, so there is a kind of collision between what the analytics says and what you can do legally and ethically, right? Okay, so anyhow, let's go ahead and run the model. Now what I'm going to do actually is remember what we did in the how did we measure the accuracy of the classification models? Remember when we discussed classification tree? We said that there is a way to judge how well your model fits the data. What was this thing? Misclassification rate, right? And also we looked at confusion matrix, right? Every time when you're running classification model like that, when your answer is supposed to be yes, no, true, false, default versus non-default, every time when you make prediction, there is a reality, right? That's how we use training data. Training data actually knows what happened in each case. And when we're training the model, we're trying to make a prediction and then compare it with what happened in actuality, and then based on that judge, is that a normal classification, yes classified as yes, no classified as no, or is it a misclassification, right? So for that, I can do it on a fully blown model, right? I can use the entire set, 5,000 observations, as my training model, right? That's what we did in the previous class. We didn't break it into the validation set and training set. Now let's do that, okay? So let's go to Analyze menu, say Predictive Modeling, right? How did we make the validation column? And click on this option, Make the Validation column. Well, let's split it 60-40, right? So 60% of my set, 0.6, I'm going to use for the training purposes of this model. And the rest, 40%, I'm going to use for the validation, okay? And so that we're going to end up with the same result. Let's use 100 as the seed value, okay? And fixed random. Fixed random means that you and I are going to end up with the same breakdown between training data and validation data, okay? So the model that we're going to construct is going to be the same exact thing. Fixed random. And it adds the validation column, right? 60% of the records are labeled as training and 40% of the records are labeled as validation, okay? All right, now I'm going to build the fully blown model. So again, I'm going to the fit model, right? And my personal loan is the target. All the other variables are predictors, except validation, right? I use validation in this place. Hold on, validation. I'm going to place it right here. Okay? And after that, immediately my jump window right there says it's nominal logistic because my target is categorical, right? Notice that if it's continuous, it's going to be least squares, right? Standard least squares method. But if it's categorical, it's going to be logistic regression. And which level do I choose as a target, 0 or 1? 1, because I'm primarily interested in people who will agree to take out a loan, right? 1. And then I click the run button, and there it is, okay? So now I don't have this plot. Remember, when we ran this model only for one predictor, for the income, I had this nice plot, sigmoid function, right, that says higher income results in higher probability of agreeing to the loan, right? Now I have more than one x variable, so therefore there is not a single sigmoid function, right? Okay, well, let's take a look at model first. Okay, so parameter estimate. Here is my model, and you can see that it's, oh my god, complicated, right? So, what does that model tell me essentially? This is it. So let me write it out. First of all, if you remember, if you were paying attention in the last couple of classes, the model essentially goes like that. Natural log of p over 1 minus p. By the way, how do we call that ugly monster? Odds, right? That's called odds, okay? Natural log of odds is equal to beta 0 plus beta 1, x1 plus all of them beta k, xk, right? That's my model. So in my specific case, it looks like that. Natural log of odds is equal to intercept minus 8.58 minus 0.0093 minus 8.58 minus 0.093 times the age. I believe the first variable is age, right? Next variable is experience plus 0.102, 0.064, so plus 0.02 times experience plus 0.064 times, I believe, income, right? And the rest of them. So the list goes on, okay? So that's essentially my main output from the regression analysis, right? It's right here. It's my parameter estimates. Okay. Now remember what we discussed in the previous class. If the slope, so all of these are slopes essentially, right? My beta 0, beta 0 is my intercept right here. This is my beta 1, beta 2, beta 3, etc., etc. Okay, remember what we discussed in the previous class. What happens if your slope for the variable for your predictor is positive? What does it do to the odds? As the variable increases, do the odds go up or do the odds go down? For the positive slope. Yeah, the odds themselves of getting a loan, are they going up or down if the slope is positive? We did that with income. Remember, the income slope was positive. So positive means what? Well, even from this equation, right? If your slope is positive, that means that if you go from x to x plus 1, your log of odds becomes higher, right? If the slope is positive, if beta 1 is greater than 0, okay? And therefore, that means that the odds are getting higher, and that means that the probability of getting a loan is also getting higher, right? So it's a very simple rule, right? From the output, how to kind of interpret the output from your regression, logistic regression. If the slope in the output is a positive number, that variable impacts the odds or probability to get a loan positively. If it's minus sign, that it impacts negatively, right? So let's take a look. Income, remember what we found in the previous model that we ran with only one variable income? Income goes up, what happens to the odds? They also go up, right? I believe we found, if I remember correctly, $165,000 was the magical number where the odds, where the probability crosses from below 0.5 to above 0.5. And we start classifying that person as 1 will get a loan as opposed to 0 will not get a loan, right? So same thing happens here, right? Income impacts the odds of getting a loan positively, okay? What else can I see? Experience also has a positive impact, right? Family size has a positive impact. Does it make sense? The larger family make person more likely to get a loan. When you have kids, are you likely to get? Yeah, right? You want to pay for education, you want to buy a car, right? So therefore, kids are good that way, right? You get more debt. Okay, credit card balance. If the average credit card balance goes up, the person is likely to get a loan. That also makes sense, right? Because if I'm using my credit card a lot, that means that I'm in need of money, right? So therefore, I'm also likely to get a loan. So that makes sense. Okay, mortgage. Mortgage has actually very low slope. Wouldn't you agree? It's positive, but it's very low, right? So it's kind of a positive impact, right? What else? CD account with the bank has actually pretty good positive slope, right? So if the person has a saving, CD is essentially savings account, right? Certificate of deposit, so in the long-term account. So that makes a positive impact. But what do we have in the negative area? Well, education, we're going to discuss that separately because education is funky, okay, this way. All right, so let's see. Age impacts the likelihood of getting a loan negatively, right? Whether or not they're banking online, if they are banking online, if it's a 1, right? That means that they're less likely to take a loan. Who knew, right? That's kind of unusual. If I'm using an online banking, like I can transfer funds between my accounts through the browser, right? And I can get statements electronically, I'm less likely to get a loan from the bank. That's kind of non-trivial, right? And it's hard to justify this thing. It just comes out of date, right? Why? Why, if I use online banking, why is it making me less likely to get a loan from the bank? I don't know, quite honestly. And same thing, credit card, okay? If the person is holding a credit card from that bank, they're less likely to get a loan, right? Because the slope is negative, okay? All right, now let's also discuss, now any questions so far? That seems to be fairly straightforward, right? Okay, let's discuss which variables are useful and which variables are useless, right? So in other words, statistical significance. Remember, we kind of touched on that in the previous class, but let's kind of review that again. What do we test? Okay, what do we test? In order to test the significance of the variables, we test this hypothesis. Now is going to be that the slope for that specific variable I can be replaced with 0, which means that the variable is not significant, right? Not significant. Okay, and alternative is going to be that the variable slope is not equal to 0, which means we can't take it out of the equation. Therefore, it doesn't really contribute much. Okay, so it's the same exact analysis as we did for the linear regression. Okay, so right here at the end, in the last column, we have the p-values listed. So if I'm looking for variables which are not significant, what do I look for? High p-values or low p-values? Low? Not significant. High, right? So if p-value is high, I'm keeping the null hypothesis, and null says that I can replace slope with 0, therefore taking out the variable out of the equation, right? So it looks like, remember we discussed mortgage just 2 minutes ago, right? Mortgage seems to have low slope, right? So therefore it doesn't seem to impact things all that greatly. And indeed, if you look at the p-value is really high, right? So therefore I keep the null for the mortgage balance, and that makes this variable really a bad predictor, right? I may as well get rid of that and not worry about the thing. Experience also is not making a contribution, and age. Remember we discussed that age has a negative correlation, right, with the likelihood. And that makes sense, right? If people get older, are they likely to take a loan out? Like if I'm 60, do I get another loan? Probably not, right? Young people who want to buy cars, who want to buy houses, boats, pay for the children education, all that stuff, right? They can take out loan more easily, right? As people get older, chance that they're not going to do it, right? But it turns out that experience is not significant, right? Okay, now let's take a look at the accuracy or goodness of fit, right? I believe it's right here in the fit details, right? Okay, misclassification. Remember when we started this whole thing, we said, let's split the entire set into training, where we build a model, right? Where we estimate these coefficients that we just looked, parameter estimates. And then there is a validation set, right? So validation, sometimes it's called, if you remember, a hold out set, right? So what I'm doing really is I'm saying I'm going to use 60% of my data to train the model, build the coefficients and whatnot, right? But then, of course, what will start happening, probably, I'm guessing, is because I'm fitting the data, I'm fitting the model into my specific training data, I will, to a certain degree, overfit the model just for that data, okay? So in other words, whatever noise I have in my training data, that probably will get reflected in my model, right? So when I take my model, which I build on training set, and apply it to another data which model didn't see yet, that would be validation, right? What can I expect in terms of the performance? Because I'm kind of capturing some of the noise which is in training set. If I apply it to a different set, this noise is not there anymore, right? So the performance probably is going to get worse. So I can expect the misclassification rate to be slightly worse when it comes to applying the model to the validation set, right? But hopefully not much worse, right? So, and misclassification rate is the one that we're using to judge how nice the model performs, right? And R squared is another thing, of course, right? But R squared has a little bit iffy interpretation. Remember R squared, when we did the R squared for linear regression, we said, what's the interpretation of R squared? It tells you the percentage of variability in the target, which is explained by variability in predictors, right? So here, I can have variability of predictors, no question about that, because some of my predictors are continuous, right? My target really is categorical, right? 0, 1. How do I measure variability for the categorical variable? It's an iffy proposition, right? Because 0 and 1 really are not 0, 1. They're agree to the loan and decline the loan, right? I just labeled them 0, 1, okay? I could have labeled them 10 and 20 or 100 and 200, right? So therefore, variability, the whole idea of variability kind of becomes very shaky, okay? So therefore, R squared is less reliable, so to speak, measure of how nicely my model fits into the data, okay? And the misclassification rate is a preferred way to measure it.
Which misclassification rate do we use? Is it like the training or the validation?
That's a good question, actually. I'd say, well, what do you think?
Validation.
Validation probably, right? Because validation, when I'm fitting the data to the training, when I'm fitting the model to the training data, essentially I'm building the model, right? I'm trying to get as close to my data as possible, right? And after that I'm saying, yep, model is done. Now let's see how it performs on the data that it didn't see ever before, So it's kind of an independent verification, right, for me. Like, is that really that good of a model, right? So therefore, it's kind of an independent set of how well my model performs, right? Moreover, sometimes, and you probably remember, when I just did the breakdown between the training and validation set, there was also certain percentages that I could enter for testing set. Remember? There were like three. Let me show you. Okay, here, right? So analyze, predictive modeling, make validation column, and here you can see I have place for the percentage on training, validation, and there is testing. What's testing? Testing, the idea basically is, remember how we built the, what's it called, classification tree. We said we use training set to grow the fully blown tree, right? Then we use validation set to prune it back to the reasonable size, right? So therefore, both of these sets are kind of used in selecting the model, right, essentially. And then what do we do? Well, we need to test it on the independently collected set. And that's where the testing set comes in. So generally speaking, we're going to break our set into three subsets. Training, where you build a model. Validation, where you adjust the model to make it good, right? Or not, to avoid overfitting, right? And then after that, you have a model, you're saying, okay, now let's try it on something else. Let's see how well it performs. And that's where your testing set comes into the play, okay? All right. So, coming back to the discussion, right? Excuse me, misclassification rate. Remember what we just discussed. When I'm building the model, I'm tending to overfit the model and capture some of the noise that I had in my training set, right? And that's exactly what happened right here, okay? I have the noise captured. So my misclassification rate is 3.97, so 4%, right? 4% of my observations are misclassified, okay? In my training set, so 60% of my data, right? And then I took the validation portion, I applied that, and I saw slightly worse performance, right? Close to 5%, 4.97, okay? It's not a drastic jump, thank God for that, right? That would be kind of bad if my training set I'm misclassifying 4% and I misclassify 20% on my validation set, right? And I'm going to say, wow, am I really overfitting the model, right? What's going on? Why is it so different? So this actually is not that different, right? But it's still worse, right? Slightly worse performance on the validation set because of that. Because when I'm building the model and using the validation, the training set, I'm really capturing some of the noise, which is not the pattern that I'm looking for, but rather random variations specific to that data set. Okay. All right. Now, what else did I want to tell you? Let's get down to the discussion of education. Okay. Education was what type of variable? Let's go back to our original thing. Categorical, right? And moreover, if I double click on the education column, it tells me that this is how things are coded, okay? 1, if a person had an undergraduate degree. 2, if a person had a graduate degree. And 3 is PhD, JD, so doctorate, right? Advanced degree, whatever that means, right? Okay, cool. So remember when we discussed the regression, okay? We had exactly the same thing, right? With cars. Car can have automatic transmission or manual, right? Or it can use diesel or natural liquefied gas or petroleum, right? Gasoline, basically. So exactly the same thing happens here. Now, here is the reminder for you, ladies and gentlemen, okay? How the categorical variables are handled every time when we have simple linear regression or logistic regression, okay? So each time when I have a categorical variable with k levels, okay, k levels, I require how many dummy variables to represent these k levels? I require k minus 1 dummy variables, okay, dummy variables. So, in my case, for example, okay, education has 3 levels, right? Education can be 1, which is undergrad, can be 2, which is grad, and it can be 3, which is doctorate, right? Okay. So to represent 3 different categories, I need how many variables? K minus 1, 2, right? So therefore, I need a variable which represents for me education level 1, undergraduate degree, okay, or education level 2, which is a master's degree, right, graduate degree, and 3 will actually be a combination of 1 and 2, right, in terms of how I encode that. So here's basically a reminder, right, how I handle that. If a person has undergraduate degree, so if education equals to 1 for an incoming customer, my add 1 equals to 1 and my add 2 equals to 0, right? 0. If incoming person has education master, so therefore I encode him as 2. Add 1 equals to 0 and add 2 equals to 1. What if they have a doctorate degree? Then both of them become no minus 1. You don't remember that? We discussed that. And both of them become minus 1 and minus 1. Okay, that's what we use to represent the missing category. Okay, so therefore, from that standpoint, really, what the model does is it kind of tends to the average level, right? So between all the customers that come in, here is the average level of education. So if you have education equal to 1, then you go up by the amount of the slope, right? So add equals to plus 1, that's your education equal to 1 customers. If education equals to 2, then you also, let's say they're both positive, you also kind of go up from this level, education equals to 2. But if it's doctorate degree, then every one of these positive numbers is multiplied by a minus 1, so it goes down, right? So this is your education equals to 3. So therefore, well, the model kind of considers the average level, right, between all the customers. And then after that, you go up or down depending on which one is it, okay? And depending on the slopes values. So let's kind of discuss that in more details, right? All right, so over here. What happens in my model if my education is equal to 1? That means that I have all this other stuff, right? Hold on. And the slope right here is minus 2.6579, right? So minus 2.66, let's call it, all right? Do I still have it? Let's see. Yeah. So I'm going to, oh, hold on. I'm going to erase all that. Here's how I can erase that. Kaboom. All right, so therefore, all these variables stay in the model essentially, but what happens after that, I'm going to say that thing, okay, my model gets an addition of minus 2.6, oh God, what was that, 658, right, 658, if the education equals to 1, if it's only undergraduate, right? If education equals to 2, that means that they have completed master's degree, my model is actually getting plus 1.524, right? So plus 1. Is it 25 or 52? 254, right? 1.254. And finally, if education equals to 3, what do? I multiply both of them by minus 1 and add them together, right? So therefore it becomes plus 2.658 minus 1.254, okay? So in other words, I'm getting that should be a nice number, easily computable, right? Plus 1.404, something like that, right? Something like that, okay? Make sense? Kind of, sort of, or not really? Now let me show you how I can actually verify if this is true or not, okay? What I'm going to do is I'm going to save the prediction formula into my data set, okay? So here's what I do. As you guessed, it's all located in the red triangle, right? So if I click to the red triangle menu and I go to save probability formula right there, okay? Save probability formula. Click. All right. Nothing happens, right? Well, because it went to my data table. So let's go back to my data table and look what happened. My last column before I built a model was validation, right? So now it added, 4 more columns, right? Linear regression part, LIN. Okay, so this beta 0 plus beta 1 x1, yada, 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 okay? Then probability that it calculates from that, probability of 1, probability of 0, and can you guess what happens if you add these two together? If I add probability of 0 and probability of 1, becomes 1, right? So that one is just 1 minus the first, right? And then based on that classification, is it a yes or is it a no? Okay? All right. So let's take a look at the formula behind this one, linear regression. Okay? So I double click on this column that says lin of yes, right? And here's my formula, and formula is gigantic, right? So my slope minus 8.8, so essentially I have the same thing as right here, right? The slope plus the intercept plus first slope times age plus second slope times experience, blah, blah, blah. But what I'm looking for is primarily that portion of my output. Here's what we figured out. If the education is 1, if it's undergraduate, then I have to subtract 2.658. If education is 2, if the person has a master's degree, then I have to add 1.254, right? And if it's 3, doctorate, JD, whatever it is, plus 1.402. Is that the case? Well, here, right? It says based on education, if 1 minus 2.658, if it's 2 plus 1.254, and if it's 3, 1.404. Is that the same thing as we had? It is the same thing, right? So that's essentially how all of that is computed based on the outputs, okay? Any questions? Is it confusing? Or handleable, more or less? It's not completely incomprehensible, right? Fairly straightforward. Okay. Now, ladies and gentlemen, let me ask you this question. Okay? Let me go back to this equation. Now remember that all of that just compute the natural log of odds. Okay? So let me erase some parts that can be confusing, right? There you go. Okay. So if I would ask you, between the people, same thing, same everything, 3 people come in, okay, today. They have same age, same experience, same income, family, credit card balance, identical, okay? But one of them is with education equals to 1, undergraduate degree only. Another is with education equals 2, master's degree. Another has doctorate. Which one is most likely to get a loan from us, to agree to a loan? Has the higher odds or highest probability to get a loan? What am I looking at? Yeah, so for example, I have these numbers, right? You're saying doctorate, right? Yeah. Exactly right. You agree, right? Why? Because, remember we discussed that positive slope or positive number, right, in the logistic regression increases the probability, right? Negative slope or negative number decreases the probability, right, or odds. Okay, so basically what I'm looking for is the highest positive number, right? Simple as that. That basically means that it increases the odds more than anything else, right? The highest positive number. Second highest positive number is my second winner, and the least positive number, in my case, is negative, right? That's the least odds, right? So therefore, what do I say? The highest odds of getting a loan belong to people with doctorate degree, right? Then, for people with master's degree, odds are slightly less, right? And people with only undergraduate degree, odds are the lowest between the 3. Make sense? How are we doing? Yay? Okay, cool. All right. Now, what I wanted to discuss, the last thing standing actually is, no, actually there are a couple of things standing. Do you want to keep that until Monday? Because it's an informational overload a little bit. What I wanted to discuss is unit odds ratio. We did that actually for income when we had this simple equation. Okay, but we didn't discuss the odds ratio for the categorical variable. So for this type of stuff, right? Plus also sometimes when the slope is negative, that means that the odds are actually getting lower, right? And I wanted to discuss the unit odds ratio for the unit odds ratio for for the slope when the slope is negative, because it has kind of slightly different interpretation. Okay, so let's leave it off until Monday. Okay, so on Monday we're going to finish that topic and we're going to start a new one, which is called clustering analysis. Okay, so on Monday we'll take about 20 minutes of time finishing up that topic and then start clustering. All right, that's it for today.